Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman, and in this video we're going to go over Aromatic Systems Part 1. Now, Aromatic Systems Part 1 is all about the properties and the things that define aromatic systems. So what we're going to focus in on are the characteristics of aromatic systems, but we're not going to focus on the reactions. That's going to be Aromatic Systems Part 2. Okay, so for the very first part, which is going to be about 3 to 4 hours long, I'm guessing, it's going to be all about doing problems related to identifying aromaticity. But also, it's going to be about, like I said, learning the fundamentals, the characteristics, what makes up an aromatic system, what's so special about them, what unique properties do they have, things along those lines. And then, like I said, after we're done with Aromatic Systems Part 1, then we'll move into the reactions. We'll learn about their specific reaction types and all the philosophy around that, and that'll be called Aromatic Systems Part 2. Alright, so let's get started. Now, as you can see, this video here, and actually let me mention this right away, that there's only a few points of problems. So I think section 3, after that we'll do the first set of problems, and then 4 and 5. So there's not a lot of problems in this chapter as far as spread out in different areas. There are going to be, I think it's like 30 problems that we're going to solve together, but it's all kind of towards the end. Alright, so get a coffee, sit back, relax, and just make sure you get these fundamental points because they really are important for the whole semester, not just for now. That's why it's important that you kind of get a good sense about what aromaticity is. Now, this isn't a hard chapter, so you don't have to worry about that, but it is going to be, you have to take this journey with me and get the full story, okay? Because it's going to help you throughout the rest of the semester. Alright. Now, the first thing we're going to do is a very general introduction, but it's actually going to have a lot of meat to it. So we're going to learn about what aromatic is, what type of reactions they go through, the structure of benzene, because we know benzene is an aromatic system, and so we're going to focus in on that for a moment, and then the stability of benzene. And just so you know, we're going to use benzene as almost like our model that's going to represent all the other aromatic systems, and there are many aromatic systems, okay? So we're going to use benzene as our model, but we can apply the same concepts to any aromatic system once you learn benzene. Alright, let's get started. Okay, let's get started by first focusing in on the difference between aromatic and aliphatic. And again, I just want to emphasize that we're going to use benzene a lot during this chapter and definitely in the next chapter, Aromatics Part 2. And just remember that benzene is just our model. Okay, think of it as benzene is the most popular model. It's a simple enough model, and it has a lot of chemistry that we focus in on a regular basis for drug chemistry, for biological based chemistry. So benzene is a good foundation to learn from, but it really, what we're learning about benzene applies to many different aromatic systems. Okay, so just keep that in mind as we go through this. Now, the first thing is, what is aliphatic, right? What's aliphatic compared to aromatic? Now, really, one way, and there's a lot of different ways to look at this, but the simplest way to explain it is that an aliphatic system is where you have more H's per carbon. So the hydrogen-carbon ratio is much greater than an aromatic. So there's more H's per carbon. That is a common theme amongst all aliphatic systems. Whereas aromatic, they either have the same number of H's to carbons, or it has less H's per carbon. And that's a huge difference. Think about it. Now, I'll give you some examples. An alkane or an alkene and even an alkyne, those are all aliphatic systems. Remember, it's CN H2N plus 2. So for every, remember, N is the number of carbons. So for every one carbon, you have 2 times N plus 2 H's. Much more H's per carbon, right? So let's say C5H12. So for every 5 carbons, there are 12 H's. All right. Now, even this one, CnH2n, for an alkene. And so, again, you have a lot more H's per carbon. And CnH2n minus 2, still a lot more H's per carbon, no matter how you look at it, right? So if this is C5, it's H10. This is C5, H8. And in all three cases, we have a lot more H's to carbon. And with an aromatic system, that's not the case. So for example, benzene, its formula is C6H6. So you have the exact same number of H's per carbon. Same number of H's to the carbon. And so that's an example. And think about it. If I have a branch on benzene, I'm going to have less H's than carbons. So that's the key difference. You see that? So aliphatic systems compared to aromatic systems. And it's pretty much, that's really how we categorize the two different types. And by the way, cycloalkane also, cycloalkanes and alkenes or alkynes, they also belong in the aliphatic section. Now, people years ago thought aromatic is about its smell, right? It's olfactory consequence or result. But it's not really true. Not all aromatic systems smell great or beautiful. So it's not necessarily true that aromatics smell pleasant. A lot of them do, but not all of them do, okay? So really it comes down to the number of H's per carbon. That's it. All right. Now, let's talk about what are some of the chemical consequences of having aromaticity, or what are some of the benefits? It depends how you want to think about it. Well, first off, again, all aromatic systems have, and this is the most broadest term that we're going to use, or the general sense, is that it has equal or less number of H's per carbon. Now, what does that actually tell us, or what does it do for us in terms of reactivity? Well, it turns out that it does something special, but it's not because of the number of H's. We'll learn all about the reasoning for this in just a few. But the most important thing is that they do not react like regular alkenes or polyenes. Remember, poly, like diene, triene, tetraene. When you have a whole bunch of alkenes, then they have a certain way of reacting. Remember the 1,2 and the 1,4 addition? So I'm assuming that you know your conjugated addition, that chapter. You've already watched that before you did this, and it really is important because you kind of extend ideas from there into this. So you don't have that. You don't have, there's no addition reaction. Now, for example, if we take a benzene, which has 3 alkenes, 3 double bonds, you would think HBr, you should be able to put at least one of them in, right? Break the double bond, put an H and a Br in. And probably even go further than that, right? It turns out this does not happen. You cannot get the H and the Br to add across a double bond of an aromatic system, of a benzene. And the question is why? And we'll see why in just a few minutes. But it's important to recognize that there is no addition reactions. Okay? Now, another thing, now, and when I say no, we're talking about under normal conditions. Okay, so let's keep that in mind. This is under normal conditions, meaning, you know, maybe a little bit above room temperature. I mean, for you to get this to happen, you'd have to really increase the pressure and the temperature in the environment, and then it probably would happen. But that's not normal conditions. These are extreme conditions that we would have to artificially insert around the system. Okay? Whereas an alkene, you wouldn't have to do that. An alkene would naturally go and break apart with HBr without very little energy. So it's, you know, within the normal range. Okay? All right. Now, as far as what they do is aromatic systems go through what's called substitution reactions. So they go through substitution reactions, meaning you can swap out something on the benzene or any aromatic system and put something in its place. So if I have, let's say, X, you know, we don't care what X is, we can remove an H and put an X in its place. So that is fine. That we can do. So we can swap something out for another piece. And that's substitution. Now, this is the next chapter. So the next chapter is all about this reaction.